Hey Jordan. Okay, I'm finally getting around to doing this video. Give me one sec. Okay, so I'm on the front page of the video or the worksheet you gave me. Notice I have the coordinate grid up here that you have for number 1. So I don't know if it's confusing, like I don't know. It's hard because you're not here to ask questions while I'm teaching, but I'm not sure if it's reading the questions, you're not sure what you're supposed to do, like you don't know what you're being asked to do. So what I would do first in this problem is I would just read it. So it says the average monthly temperature for some town in Michigan is shown in this table. If I look at this table, they give me one temperature per month, and they tell you at the top it's the average monthly temperature. So they averaged the temp for all the days in each month and gave you the temperature. Okay, that's fine. So then it says use the data in the table to answer the following questions about modeling real-world data with a sinusoidal function, which is a mouthful. All that means is it's a sine function. So that sentence really is not very useful. So we know we're going to use this data for the rest of the worksheet, but that's about it. All right, number 1. On the graph below, plot the average monthly temperature. So that's all you need to know. So let's just look at that. Plot the average monthly temperature for that town in Michigan. Well, do we know what the average monthly temperatures are, or are we going to have to do calculations to find them? That's the question. So when it says plot the average monthly temperature, I'm going to have to plot points on this coordinate grid, clearly. I just don't know if I can just plot things I'm directly given, or if I have to solve for numbers and then plot them. So you have to ask yourself, do they give you the average monthly temperature? The answer is yes, they do. They give you the average monthly temperature for every month. So we're just going to plot all those numbers. It says over a 2-year period. So we're not just going to plot these 12 numbers. We're going to plot how many numbers? Should be 24 because we have 24 months in 2 years. So we're going to plot these 12 numbers for 1 year, and then we're going to plot them again for the second year. It says let x correspond to January. So if x equals 1 is January, then 2 would be February, 3 would be March, 4 would be April, and so forth. And we're just going to keep going. So we're going to go ahead and plot these points. In his really weird coordinate plane that he gave you, where the x-axis numbers increase by 4 or by 8 each time, it's just really weird to me. But that's okay. So actually, it would be good if you just paused the video and plotted these points, and then came back on to make sure it matches mine. Mine's going to be a little weird because I don't have like an actual coordinate plane. It might be a little off, but so go ahead and plot. That's the first thing we gotta do is just plot this. So this is like geometry 101 here. Okay. So x equals 1 is 30. January is 30. So you just estimate because it's kind of weird the y coordinate plane thing here. 2 is February is 33. March is 42. So 3 is March. And if you want, you can label these like January, February, March, April, May, June, July, August. If it helps you, you can do that too. April, 57. March, whoops, May, sorry, 69. It's early for me here. 69. Yeah, mine probably are a little off here. I'm not doing a very good job of lining them up either. Okay. June is 78. July, 82. August, 80. Okay. Man, my thing's a little off here. August, September, October, November, December. Okay. September 73. October 60. And mine, hopefully yours looks better than mine. You have lines to follow at least. My goodness. 46. December 34. Okay. Okay. All right. So I plotted January through December, so the first 12 months, and then we have to do another year. So we're going to repeat all of these again. So here we go. We're back to January, February, March, April, May, June, July, August, September, October, November, December. Okay. So I'm actually not even going to look at the chart. It'd just be easy to copy these over. So this one should line up. And then the second point should line up. February. Third point, March. April should line up with April. May. June. This looks funky, I'm sorry. It's difficult when you're close to the board. Let's see. Man, mine are really weird. Okay, mine are a little off. They got shifted. That's okay. Okay. Actually need one more. Wait. Something screwy here. Let's see. 1, 2, 3, 4, 5. Okay. All right. So I have both months. This one's a little smaller for some reason. Then this one is a little wider. They should be the same on yours. Hopefully you're better at doing this than I am. That's pretty much it. So we should just connect the dots here. Okay. Now these should look the same size. Mine do not. But you can imagine how they should look. Okay. So that answers number 1. You're done with number 1. Number 2 asks you, does the graph of the data from problem 1 appear to be that of a translated sine function? So you've been working with sine functions and cosine functions, hopefully, in your class. So the first word in this question that maybe you don't know is translated. You kind of know what translated means. We learned translated functions. We didn't do sinusoidal functions, but we did translated figures in geometry. It was a type of transformation. And the word translated you also know from probably just the English language in general. If you were to translate something in Spanish into English, you are transforming it. So for instance, bien in Spanish, if I were to transform it or translate into English, it would turn into good. So a translated function is just, you're changing it. It's a change. In a sinusoidal function, you're changing it, meaning you're moving it, it's shifting. So does this look like a sine function that's been kind of shifted or moved? It's been translated. Well, you have to know what a sine function looks like, and hopefully you recognize this as a sine function because it has a sine wave. So sine and cosine functions should be a wave, if you've noticed that. And then the tangent function has those asymptotes in it. And so a tangent function would have those asymptotes, and you get something more like that going on. You can also get parabolas and tangent functions. So this looks like a sine function. Now, if you remember from, hopefully you've been taught this, sine functions normally cross the 0, 0 axis, right, where the x and y axis meet. And this one does not. That's okay though, it's been moved, it's been shifted, it's been translated, it's still a sine function. And then the standard cosine function crosses at 1, and it doesn't cross the x-axis at 0. So that's the difference between sine and cosine. One difference, there's a few differences, but this does look like a translated sine function. It has the right shape. You have 2 periods, you have 2 years, and it's repeating itself. So it looks like a sine function. If we go to the second page, it says the highest average monthly temperature for this town in Michigan, I have no idea how to pronounce it, Charlevoix, is 82 degrees Fahrenheit in July. The lowest temperature, average temperature, is 30 degrees in January. And we have that. So we have the lowest being 30, right? This is also 30. Anytime you see January, we don't have January there. And the highest is 80 in July, which we have. Okay. The average of these two temperatures, so if I were to find the average between these two, what would I do? What would I do to find the average? Like any other average problem, you just add them together and divide by 2. So average of anything, you add them together, divide by 2, and it says you should get 56 degrees, which you do. So the average is 56 degrees. Plot the function y equals 56. If I have the function y equals 56 degrees, and we did this in geometry, how do I plot that? Remember, we have when we plot lines, it's y equals mx plus b. But what if we don't have an x and a b, and we just have y equals a number? What do we do? Well, it's simple. You just find 56 on the y-axis, and you draw a straight line. Remember, y equals something, y equals a number, is a horizontal line. I don't know if you can see that. Sorry, I'm like going all over the place. And then x equals a number is going to be a vertical line. So if I have y equals 56, I find 56 on the y-axis. Sorry, I'm moving you around here. I find 56 on the y-axis, and I just put a line in. That's where 56 is. Now you can put like just a regular old line in there too. If it had been x equals a number, you would find 56 on the x-axis and draw a vertical line. Okay? All right, so now we've drawn this line, and it's asking us, in terms of a sine function, what does this line represent? What does it represent? Now, you might not know the term. Maybe you do. Hopefully, you've been taught the terminology. If not, just think about like what it looks like it's doing. What does it look like this line is doing? Even if you don't have any clue what it's doing, we know what it represents. It represents this, which is what? That's the average. If it's the average between the highest point and the lowest point, it's the exact middle. It's like slicing this figure in half. And so you almost have, it's not a mirror image, right? It's almost like the opposite. Because it's not a mirror image. Because if it were a mirror image, this hump, you'd have a hump down here, and you don't. So it's not a mirror image, it's cutting it in half. Since it's not a mirror image, we actually call it, an inflection point. It's not reflecting a mirror image, it's inflecting it. So this is a mirror image of this. It's kind of like an inflection point. That's what we call this line. In case you don't know the terminology. This line is called inflection point. If you ever forget the term, it's fine. You'll get credit, most likely. If you just understand the concept, then you can describe what inflection point is. So you just describe it in words. It is the average among the highest point and the lowest point in my sinusoidal wave. And you can describe how it cuts it in half, meaning that this distance from this new line, it's kind of like your new x-axis, is the same as this distance from the top of this crest to the bottom of it. These are all the same distances now. They're all the same. That's what it means by cutting it in half. So you're taking these waves, you're cutting them in half so that they're still the same. They're still equivalent. Okay, let's move on to number 4. So using the graph, calculate the amplitude, the period, and the phase shift of this translated sine wave. So we're going to go ahead and do that. There aren't really calculations. I'm not really sure why they put that there, but I'm going to erase some of this stuff. So there's more room. Okay, here's our wave. All right, so amplitude is, you need this inflection point to find amplitude. So amplitude is basically taking the top of your wave and the bottom of your wave, and you divide it by 2. So this whole distance from bottom to top, what is that whole distance? Well, we know the bottom is 30, and the highest point is 80. Actually, the highest point is 82. I'm not sure why they... Oh, they did say 82, okay. So the highest point is 82. Sorry, I screwed this up. I said 80. Should be 82. The highest number in your chart for number 1, and they did say 82 in problem number 3. I just read it wrong. All right. So if your lowest point is 30 and your highest point is 82, well, what's 82 minus 30 to get this entire length distance? Well, 82 minus 30 is 56. Wait, I mean 26, sorry. Let's just do the math. So 82 minus 30, sorry, I was like looking at something else. 2 minus 0 is 2, 8 minus 3 is 50. So we get 52. Trying to think what I did, because I didn't do this. Did I do this right? Yeah, okay, I think I did. Okay, yeah. 52, so this entire distance is 52. 52 units, and our units are degrees, so we're just going to say degrees. I don't know if you can see that. Yeah, you can. Okay. So we need to know what the amplitude is. Well, the amplitude actually isn't this entire distance. It's the distance from the inflection point to the top peak or crest, and the distance from the inflection point to the bottom peak or crest. But since these are the same, you just need to know one of them. They should be the same. So 52 divided by 2, you should get 26. And so this distance is just 26 degrees. So this whole crest of your wave from bottom to top is 52 degrees tall. And if you divide that in half, from inflection point to peak or crest is 26 degrees. 26 degrees, 26, 26. And every wave is the total of 52. So your amplitude would be 26. Okay, period. Is that the next thing they want us to find? I'm trying to think here. Okay, period. Distance from one common point to a similar common point on the graph. For example, from crest to crest. So you find one point in your graph. Let's say we pick the crest. Usually the crest is really easy. Well, where's the similar point on the graph? Well, we find the crest again right here. So that's going to be my similar point. You just find the exact same point. What's this length? So now we're looking at the x-axis, not the y-axis. So what is this distance on the x-axis? Let me get rid of some of this. So from here, this is July, I think. Yeah, sorry, my graphs. July to July. What's that distance? Oops. Well, we go from, this is number 7, 6 and 8 are on either side of it. So this is number 7 to number 19 on our graph, on our x-axis. Well, what's 19 minus 7? So you get 12, and it makes sense that's 12 because, remember, the period is just 1 year, and we did 1 year 2 times. So it's 12, because there's 12 months in a year. So that's what happened. So that's why the period is 12. It won't always be that simple to just think like, oh, a period's a year, because we're doing 2 years, and so it's just 12, because there's 12 months in a year. It won't always be simple data like that, so it's really good to just find a point, find the x-axis, count how many to the same point later on the x-axis, and then subtract them. So 19 minus 7, and we got 12. Okay. Next thing we need to do is, what does it ask? Phase shift. Horizontal shift of the graph from the basic sine graph. Find the value to the nearest month. Okay. So we're going to go to the nearest month. And the reason I said to the nearest month, like to round it, is because we don't have any months, any points, touching our inflection point, our inflection line. So we're going to have to round to the nearest one. And the nearest one looks to be like right here. This one's really close to the inflection line. Remember, on a typical sine wave, your sine wave should go through the 0, 0 point. And ours does not, right? So these points right here should go through the x-axis, which is right here, right? But they don't. And so we need to shift this entire graph so that this point right here, this point where our graph intersects the x-axis, is actually right here where our graph would intersect the x-axis. So what is that shift? Well, this point right here looks to be at about 4. This is our 4th point right here. Our April point, our April plot, which is like 57, yeah, is really close to this point. So it's about, we shifted about 4 over to the right. So we shifted our graph 4 to the right 4 months. Okay, that's the phase shift that occurred. We also shifted our graph temperature-wise, but it didn't ask for that, so we're not going to worry about that. Okay, number 5, using the data, determine a function in the form f of x equals a times sine, parentheses kx minus c plus h. So I'm actually going to erase the graph. Okay. I kind of write mine different here. Same thing. This is kind of how I teach it with this equation. Same thing as what he gave you, just different letters. So what he gave you was f of x equals a times sine k minus c plus h. So this a and the same, both of these a's represent an amplitude. C, both these c's, both of them, represent phase shift. There's a minus sign in there, so what that means is if it's a positive number and you plug it in, it's going to be negative. If it's a negative number and you plug it in, the sign's going to change to positive. So keep that in mind, it's going to be opposite. And then this D represents vertical shift. Okay. So we're going to look at our graph, and we're going to look at this information up here, and we're going to figure out what's going on here. So this B and this K is for if your graph sine wave, let's say it's like this, were to shrink and for the same distance become like that, or become wider, so like this, that's where B or K comes in. So it's looking at more multiplicative or divisory properties, which this problem doesn't actually have, but you might in the future. So keep that in mind. Okay, so our amplitude was 26. So plug it in for A. Sine, we don't have a B in this case. X stays the same, it's just X, so you plug that, what you plug points into on your graph to solve. Your phase shift, remember, was 4. So we're going to plug in 4. It's a positive 4, we move to the right, so it's going to be negative. Just plug it in, it's going to be opposite sign. And then remember our vertical shift was 56. Now, the reason it's 56 is because when we had our sine wave up here, remember our new line was at 56. Our sine wave was up here. And remember, this line should be in the 0 axis. And so we shifted our graph vertically 56 up. So that's where that 56 came from. The last problem is really just you using this formula here to plug in numbers and plot the same thing, hopefully, that you got in problem 1 that we did together. Whoops. So you should get the same thing. So yeah, go ahead and do that, and hopefully this helped. Sorry it was so late. But again, if you have any more questions, let me know. I have a whiteboard again. We just moved buildings at work, so we were in the process of moving. But yeah, okay, good. So good luck, Jordan, and keep in touch. Let me know if you need anything else.